Helmi.
Hi, I'm Rebecca Janna binti Kamar Nasli.
Hi, I am Shaila binti Hussein.
In this video, we will conduct an experiment about electrochemical cell. What is electrochemical cell? An electrochemical cell is a device or a mechanism that can either generate electrical energy from a chemical reaction or utilize electrical energy to produce a chemical reaction. The function of the electrochemical cell to convert the given energy stored in the constituent half reaction into electrical works is enormous as well as fundamentally significant. Electrochemical is a system that utilizes a spontaneous oxidation-reduction reaction to pump electron through an electrical circuit. In the half cell where oxidation occurs is called the anode, and the electron in the half cell where reduction occurs is called cathode.
I'm going to introduce the chemicals and apparatus that we are going to use in this electrochemical cell. Okay, this is the chemicals, which is potassium nitrate, zinc sulfate solution, and then copper sulfate, and the last chemical that we are going to use is ferrous ammonium sulfate. And the apparatus that we are going to use is electric zinc strip and copper strip, iron nail, salt rich paper, sandpaper, and high resistant voltmeter.
I'm going to show you how to clean the strip, which is zinc strip and copper strip. To show you how to prepare the salt bridge in this experiment.
So we finish.
The first step in this experiment is we have to connect this wire, the alligator clip, to the voltmeter. And then we have to clip the alligator clip to the strip.
So now I'm going to show you how to set up the apparatus for zinc copper electrochemical cell. Now we are going to put the salt bridge between the two solutions. The end of the salt bridge will be in the zinc 2-sulfate solution and the other end into the copper 2-sulfate solution. We are going to turn on the voltmeter to DC, and then we have to put the strip into each solution at the same time.
For the iron copper electrochemical cell, we are going to use a different chemical solution, which is ferrum ammonium sulfate and copper 2-sulfate. The reason why we use ferrum ammonium sulfate is because we are going to use iron nail.
Okay, before we conduct the experiment, we're going to put our salt bridge in this solution. Okay, first we're going to turn on the voltmeter first. Okay, and then we're going to put our copper strip and the iron nail at the same time in the solution. in this iron zinc electrochemical cell, we're gonna use two solutions, which is ferrous ammonium sulfate solution and also zinc 2 sulfate solution.
Next, we are going to put the salt bridge between the two solutions. The one end to the ferrous ammonium solution and the other end into the zinc 2 sulfate solution. Now we are going to turn on the voltmeter into DC.
And put the strip and the iron nail at the same time.
In this experiment, one thing that we need to be more alert is on the voltage readings. Before we started the experiment by dipping the strips into the solution, we must connect the wires to the right terminal. For zinc copper electrochemical cell, the black wire must be connected to zinc strip and the red wire must be connected to copper strip. Next, for iron copper electrochemical cell, the red wire must connected to copper strip while the black wire to the iron nail. Moreover, for iron zinc electrochemical cell, the black wire must connected to the iron nail and the red wire connected to the zinc strip. All of these conditions must be followed so that the positive value on the voltmeter will be shown. If the voltmeter is showing a positive value, then the spontaneous direction of electron flow is from the black wire to the red wire. Electrons flow from the anode, which is the electron will be released, to the cathode, which is the electron receiver. If the voltmeter has a positive reading, the black wire is on the anode and the red wire is on the cathode. We need to use DC or direct current when reading the voltmeter because the DC voltmeter measures the peak value of the voltage. The DC voltmeter also consists of attenuator, which is a device consisting of an arrangement of resistors which reduce the strength of the voltmeter. Direct current also do not require a rectifier, which is an electrical device that converts an alternating current into a direct one by allowing a current to flow through it in one direction only. Moreover, the sensitivity of DC is very high, unlike AC or alternating current. Last but not least, in this experiment, we applied the DC circuit, so that is why we have to use the direct current voltmeter.
In this experiment, we have to determine which one of the strips and the iron nail is the anode or cathode. We can determine the cathode and the anode in this experiment by using the standard reduction potential SRP. Based on SRP, the higher the position of the elements, then it is an oxidizing agent, which means it's going through a reduction reaction. If the position of the elements is lower, then the element is a reducing agent and it's going through an oxidation reaction. So the electrode where the reduction occurs is the cathode and the electrode where oxidation occurs is the anode.
Nice legs, Daisy Dukes makes a man go. That's the way they all come through like.
In this experiment, we will also be counting the cell potential. But first, we have to know what is cell potential. Cell potential is the measure of the potential difference between two half cells in an electrochemical cell. The potential difference in the experiment is caused by the ability of electrons to flow from one half cells to the other. The cell potential is measured in voltage capital V, which can give us a certain value to the cell potential. There are also a few factors that can affect a cell potential in this experiment where the measurement will not be the same as the cell potential in the standard condition. The first one is the temperature, where the standard temperature is supposed to be 25 degrees Celsius, but we conducted this electrochemical cell experiment in a lab with air conditioning.
The second factor that affects the result is the molar of the chemical that we use in the lab. In the standard procedure, we're supposed to use 1 molar of the chemical, but in the experiment, we just use 0.1 molar of the chemical. With this, it will affect the result, as the result may not be the same in the theory. As for the zinc metal, copper metal, and nail, we have to clean them with a sandpaper. This is because we have to remove the corrosion and
oxidation, we are able to construct the electrochemical cell for zinc copper, iron copper, and iron zinc. We are also able to determine the net cell potentials for all the three electrochemical cells. Lastly, from the experiment, we learned that oxidation-reduction reaction can occur at the same time, where oxidation occurs at anode and reduction reaction occur at cathode.
I'm holding on your rope, got me 10 feet off the ground. And I'm hearing what you say, but I just can't make a sound. You tell me that you need me, then you go.
For the second data treatment, we have to calculate the standard cell potential or E cell for every experiment that we have done. For part 1, which is the zinc copper electrochemical cell, the anode is zinc. Zinc releases 2 electrons and it will oxidize. The cathode is copper. Copper gain 2 electrons and it will reduce. The overall cell reaction is written like this. And we got the E cell or cell potential value is by using this equation, which is E cathode minus E anode. For E anode or oxy, the value is negative 0.76, and for E cathode or reduction, the value is 0.16. So the total cell potential is when 0.16 minus negative 0.76, which is equal to 0.92. You can get the value of standard potential for every ion in the standard reduction potential table. For part 2, iron copper electrochemical cell, the anode is ferrum. Ferrum will release 2 electrons and it will oxidize. The cathode is copper. Copper will gain 2 electrons and it will reduce. The overall cell reaction is written like this. The value for E anode is negative 0.44 and the value for E cathode is 0.16. So the total cell potential is when 0.16 minus negative 0.44, which is equal to 0.6. For part 3, iron zinc electrochemical cell, the anode is zinc. Zinc will release 2 electrons and oxidize. The cathode is ferrum. Ferrum will gain 2 electrons and it will reduce. The overall cell reaction is written like this. The value for E anode or oxidation is negative 0.76 and the value for E cathode or reduction is negative 0.44. So the total cell potential is when negative 0.44 minus by negative 0.76, which is equal to 0.32.
Don't stop the party. Don't stop the party.
Hey, my people. These niggas.